Hi, I'm Jiawei from UT Austin. Today I will talk about our work at STOC 2023, Pandora box with non-obligatory inspection, Hardness and approximation schemes. This is a joint work with Hu Fu from Shanghai University of Economics and Finance and Daogao from University of Washington. So first I want to mention there is also concurrent work in STOC 2023 with a very similar title, Pandora box with non-obligatory inspection of the structure and p-task. This is a paper by Heidi Bihagi from Carnegie Mellon and Linda Tsai from Princeton. So they also obtained a very similar result as us. So we also encourage you to watch their video. So let's start with the classical Pandora box problem. This is a model proposed by Wiesmann in 1979 and is used to model some sequential search problems. So it's called Pandora box. So you start with some box, and each box has a random value. So box I has random value vi. And from the outside, you only thing you know is the random distribution of the value. Okay, you know the random distribution f. Okay, get full information. And you also know the search cost. So what is search cost? So from the outside, the box is closed. You don't know the value. Yeah, but once you pay the search cost, like if you open box 3, you first pay a search cost of 7, then you will know the true value. The true value, like V3, will be drawn from the box. And in the classical setting, we assume all the values are independent. And in the end, you want to maximize your payoff or expected payoff. And your payoff is the max opened box value. Yeah, we assume you can only take one box away. So you will take the one with the max value. And you have to also minus all the search cost paid along this way. So in the classical setting, it's used to model, you can use to model some sequential search problem. And for example, there is a big company and they want to invest some money on doing some research for new technology on their new product. Okay, so now each box is a potential new technology. And first, you have to first open the box, pay the money to do the research. Then you can know, okay, how that technology turns out, how good it is. Okay. So in this case, it makes sense that you have to first pay the search cost. Then you can take that box. Okay. Only open box can be taken. However, there are some other sequential search scenario. Like one example we like is, suppose you are a graduate student and now you get a lot of offer from schools and you can only like pick one school to go. So now opening a box is paying a campus visit. So each school is a box, but for now you only like roughly know how good it is. You have a distribution, but to have a certain like evaluation of that school, you have to first pay a campus visit. Well, but if you already know some school is your dream school, okay, it has very good distribution, then this campus visit is not necessary. So in the other word, you can take that box, take that school without inspection. So in this setting, we give you one more possible choice. It's just take the box without inspection. So this more flexible but still natural generalization is called Pandora box with non-obligatory inspection, or we call this PNOI for brevity. So our paper focused on this model. So for the classical model, there is a very simple index-based policy. This is proved by Wiesmann. And this index-based policy I want to mention is in fact a special case of Gatti's index algorithm for the Bayesian multi-arm bandit, but this is realized later. For the PNOI problem, the quest for the optimal policy is much more involved. So in a paper by Duval in 2018, in this paper, she gave a lot of simple example instance of POI show that, okay, many policy you can come up with are suboptimal. So there are always counterexample, including this index-based policy. And the best algorithm results before our work is by Guha, Managala, and Sakar. They give a 0.8 approximation algorithm. Okay, now we mean the algorithm is polynomial time. Right? If you have infinite time, then you can always calculate the optimal policy. Yeah, so the first main result of our work is we show that actually to compute an optimal policy is NP hard. But it's not that hard. Yeah, this problem is like complexity is not that high. We show that the disserver is actually in NP. So for now, the formulation of this problem is kind of optimization problem. But you can define it as a discern problem as we ask whether the optimal expected payoff is above some threshold. So now it's a discern problem. And we show that discern problem is in NP. And the second result of work is a p-task. So we show that for any constant epsilon, we can find a polynomial time algorithm compute a 1 minus epsilon approximation optimal policy. Okay. So our work almost closed the gap. So to compute an exact optimal policy is hard. Yeah, but you can approximate arbitrarily good in polynomial time. And I want to briefly mention more related works. Yeah, because there is an interesting story behind this. So the paper by Guha, Managala, and Sakar, this paper appeared in a conference on wireless communication. Okay, it's not in the econ CS or AGT community. So this paper was largely unknown to the CS community who may study Pandora box problem. Okay. And another interesting fact is that their 0.8 approximation algorithm don't even appear in the published version. Okay. And in 2018, Duval reproposed this problem and studied the property and gave like many examples show that many algorithms suboptimal. And in EC paper in 2019 by Bihagi and Klingberg, they drew a connection of this problem to the adaptivity gap, and they gave a simple y minus 1 over e approximation policy. So this policy is simple, but y minus 1 over e is roughly 0.63. So it's not as good as the 0.8 approximation algorithm. And both Duval and Bihagi Klingberg doesn't know the existence of the paper by Guha, Managala, and Sakar at that time. And very recently, there is a concurrent work we mentioned at the start by Linda Tsai and Haida Bihagi. So they independently obtained a p-task for the PNY problem, and they also showed the NP membership. It gave a structured result of how the policy looks like. And this will also in STOC 2023. Yeah, but we want to mention our work also have one more result, is NP hardness result, which show it's NP hard to compute the exact optimal policy. So first I want to mention the index policy. So what is index? Index, we use notation tau I. Okay, tau I is index for box I, is a solution to the following equation. So you can like take a pause to read this equation. Yeah, but the meaning of this equation is that this tau I, you can understand it's like a threshold. So suppose you already opened some box and already get some value, okay? And if the max value you already get is tau, okay? It's tau here. And you want to know whether it's still profitable to open box I. Okay, so on the left is expected increase of your max box value, right? Once you open box I, your new max value is max of Vi and tau I. So your increase of the max value is, okay, Vi minus tau I and take the max with 0. So this notation means take max with 0 and take expectation. And if you minus CI is a search cost. Okay, so if the equality holds, means your expected increase of your max box value just exactly canceled the search cost to open this box. So this tau I is a threshold. If your current largest value is below tau I, then your expected increase of your max value will be larger than the search cost of that box. So it's still strictly profitable. But if your current max box value is greater than tau I, then your expected gain of opening this box is smaller than a search cost. So it's not profitable to open that box. So this is one way to understand this index. And this might show there is a very simple greedy algorithm based on index. We call index policy is optimal. So let's just say this index policy by an example. So this is an example from Duval paper in 2018. So there are two boxes, A and B, and box A can take value 1 with probability 0.25, value 2 with probability 1/2, and value 5's probability also 0.25. When we assume the search cost or the inspection cost of this box is also 0.25. And here the reservation value is just another name of index. So in some paper, in some literature, it's called reservation value is 4. So why this value is 4? So you can, think this 4 as a threshold, right? I just tell you. So if you already opened a box of value 4, you already had a box with value 4 in your hand, and now you want to know whether it's profitable to open box A. So if you open box A, if you get value 1 or 2, then this box A is useless, okay? But if you get a value 5 with probability 0.25, then you increase your current max value by 1, right? So you can increase your current max value by 1 with probability 0.25. So your expected gain of your max box value is 0.25, which is exactly equal to the inspection cost. Yeah, and you can also verify for box B, the index or the reservation is 2.5. Okay. And the index policy is a greedy. It's just open the box one by one from the largest index value. So you first open box A because box A has largest index. And if you get value A equal to 5, then you should stop, right? 5 is the best value, and 5 is greater than the index of box B, right? So you should stop because this is a threshold. You already have a value greater than the remaining threshold, 2.5. Then it's not profitable to open box B. You should stop and take A. Otherwise, if you take value 1 or 2, 1 or 2 is smaller than the threshold, the index of box B. So it's still profitable to open box B. Okay, so you'll open it. And then in the end, you will take the better of A and B. Okay. But this is for the classical setting, this will be optimal. But if we, in the POI, if we allow you take a box without opening it, you can do actually better. So the first step, you will open box B. So box B will have lower index. And if box B reveal a value equal to 3, then it's still profitable to open box A because 3 is smaller than index of box A. Okay, and then you will take the bets among A and B. Otherwise, if box B gets value 0, then you can just take box A. You don't need to ever open it, right? Because if you already get a value equal to 3, if you in this time you just take A, your expectation is not greater than 3. Okay, so if you take a box without opening it, you just take it and you lose everything you already have. Yeah, but if you have nothing to lose, why you still need to pay the search cost? Just take it, which is better. And you can do the calculation. In this case, if you allow take a box without opening it, this is optimal policy, slightly better than the index policy. And here is a slightly more complicated example. So the index policy is same. Just open the box one by one from the one with the largest index and decide when to stop. So when you should stop is very natural, right? Once you already open the box value that is larger than all the remaining index, then you should stop, right? Because in that case, it's not profitable to open any more box. Yeah, but if there are still box with higher index than your current best value, then it's still profitable. You should continue. So this stopping rule of the index policy is very simple. Yeah, but here the optimal policy could have more complicated structure. Yeah, I won't explain it in detail. You can check this graph and pause and check it makes sense. Yeah, but one thing I want to mention is there is no fixed order to open this box. Okay, so it's the order of opening those boxes can be adapted. So it means the optimal policy maybe it can have some complicated structure, right? In that policy, you have a fixed order to try those boxes. Okay, but for PY, there's no fixed order, so you cannot like define a different kind of index for it. In this case, you first open box C, and depending on what you get from box C, you may first tick box B or first tick box A. Okay, you can like pause and check this example. It will make sense. Now I will mention what will the structure of the optimal policy of the POI actually looks like. So it could be adaptive, but not that adaptive. So it's more complicated than the classical setting, but not very complicated. So the optimal policy will still have an initial order pi. So initial order over all the box. So what you will do is try open each box in that initial order. Yeah, but sometimes you will switch. So there will be a threshold value at each step. So once you get a value that is large enough, then you will switch to the index policy. If not, you keep on the initial order. So at each step, you will check whether my value is greater than a threshold, a certain threshold. If it's greater, then you switch to the index policy and never come back. Okay, you execute the policy, index policy to the end. Otherwise, you continue. And in the end, you may take a box without opening it. All right. So this is the structure of the optimal policy. So this may show why this problem is in NP, why at least the derivative is in NP. Okay. Because there is a short witness. Okay. A short witness is a succinct description of the optimal policy. The optimal policy will consist of the initial order and the threshold of each step. So given this optimal policy, this succinct description, then you can like use some dynamic programming on this kind of tree graph and calculate the expected payoff. So you can verify. So this show, okay, the decision tree of the optimal policy won't be like arbitrarily complicated. Yeah, it's slightly more complicated than the classical setting. Now I will briefly introduce how we get our hardness and p-test result. First, I want to mention computational hardness result for this kind of online optimization problem are kind of sparse in the literature. And in a very high level way, our NP hardness reduction is similar to this work, optimal ordering in profit inequality setting by Agarwal, Seth Raman, and Zhang. So our plan is to first try to distill the hardcore of this problem because the general instance still has more complicated structures, more difficult to deal with. So let's start with some simple model. So in the Guha paper, okay, they show that if the value distribution is supported on 0, 1, so each box only take value 0 or 1, then this is easy. The optimal policy can be computed efficiently. Okay, so this is too easy. So we make this slightly more complicated. Okay, now each box could take 3 possible values, 0, 1, or 1/2. And we made some further constraints on the parameter. So we set the parameter such that expected value of each box is smaller than 1/2. And we also make the index is greater than 1/2. So you can set the parameter to specify this. So now let's consider the optimal policy for this kind of instance. So if you see a value 1, this is the best you can get. Okay, you should stop do any more searching, right? You already get the best value. If you continue, you will only pay more search cost. And if you see a value 1/2, notice that 1/2 is greater than all the expected value. So you will need not take a box without opening it, because if you take a box without opening it, you will in effect get the expected value of it, which is smaller than 1/2, but you already have 1/2. Okay. And we know the index is always greater than 1/2. So after you get 1/2, you should switch to the index policy. Okay. Still try remaining box. And you can also show that a box is taken without inspection only if this box is the last one. Right? Because if you can regret, then if you take a box without opening, then in effect you get a value smaller than 1/2. Yeah, but then you will regret because you know, oh, I still have remaining box with index greater than 1/2. In expectation, if I can still continue, then I should try more box. Okay, so intuitively you can show that in this way you can believe, okay, you will first try all the box except the last one. If you in the end you have only one box remain, then you will open it. So this is a structure of the optimal policy of this kind of instance. So the only thing we don't know, we haven't certain, is initial order, right? Okay, what if we always get value 0? Okay, then there is an initial order. And the initial order actually turns out it's hard to find. So we reduce from the partition problem. Partition problem is a classical NP complete problem. So give you n positive integer S1 to Sn and ask you whether it can be partitioned into two subsets of equal sum. And I won't introduce result. I won't introduce how in detail how we do this, but we managed to get like n+2 box, and box 1 to box n corresponding to each number of the partition instance, and we have 2 more special box. And in the end, we can make the initial order of those box corresponding to a partition of those integers. And we tune the parameter. Okay, some very dirty calculation here. And we tune the parameter such that the optimal solution or the optimal initial order of the POI problem corresponding to an even split of the partition problem, if an even split is possible. Okay. And also I will very fast mention the PITAS result. So the PITAS result heavily depends on the framework by Fu Li and Xu in 2018. This paper gave a very generalized framework to get PITAS for various stochastic optimization problem. And our PITAS is built upon this framework. And the concurrent work by Linda Tsai and Heidi Behagi also use this framework. But the trickiest thing is, okay, it's easy to to cast our POI problem in their framework called SSDP. Yeah, but the difficult part is to do a discretization. So because our box value could have many possible value, could be like exponential large, but have very low value, some very dirty color case. So the most difficult part is to discrete the box value to such that there are only constant many of box value possible. Okay. So this discretization is the most tricky part. Okay, so in summary, we almost close the gap in understanding the computational complexity of POI, right? On the one hand, we show, okay, to get an exact optimal policy is NP hard. On the other hand, we show, okay, we can get any y minus epsilon approximation for any constant epsilon. Yeah, so one still remaining problem is whether we can get f pitas, because our algorithm dependence on the epsilon is exponentially worse. So it's not practical at all. And there are also many other interesting setting or interesting derivation of Pandora box problem people have tried. And here is a reference list. And that's it. Thanks for listening.